Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will be talking about post-critical buckling due to shear and how the concepts developed in post-critical buckling is applied for design of tension field action as per IS 800-2007. We have so far discussed that when a load is applied at a plate girder, the one that you see is a simply supported plate girder with a concentrated load at midspan. When a load is applied, at that location, stiffeners are placed at critical zones to resist shear buckling. What you see is a load-bearing stiffener because it is placed directly under the load. Such load-bearing stiffeners are also placed at the support conditions, which we call it as end post at both support conditions. And then there are something known as intermediate transverse stiffeners. These intermediate transverse stiffeners are simply provided to provide resistance against shear buckling, and it is mainly to improve the shear buckling capacity of the webs and to introduce what is known as tensile field action. What you see as the picture below is basically the girder that I tested as a part of my master's thesis work at National University of Singapore under the guidance of Professor N. Shanmugam and Professor Devendran. The research publication can also be seen below. This is a curved girder, but nonetheless, the effects of tension field action and the band formation can be easily observed in the picture shown below. Plate girder with slender webs carry higher loads even after a web plate reaches critical stress due to post-critical buckling strength. So, the shear buckling strength of the web is a combination of two factors. The V ultimate is equal to V critical plus VTF. The V critical is obtained from the elastic critical buckling stress of the plate under shear loading, and V critical is basically the shear force corresponding to web buckling. That is equal to shear area into the critical buckling stress in shear, which is equal to AV into tau critical E, which is also equal to D into TW, which is the shear area into tau critical E. Here the tau critical E is the elastic critical stress of the plate under shear loading, which is defined as K sub V into pi square E divided by 12 into 1 minus mu square divided by D by TW the whole square, which is basically the slenderness ratio of the plate. The depth of the plate is D, which is basically the web depth, and T sub W is the thickness of the plate. And here Kv is the elastic plate buckling coefficient under shear loading, and E is the modulus of elasticity 2 into 10 power 5 Newton per millimeter square. Mu is the Poisson's ratio defined as 0.3 for steel sections. D is the depth of the plate and TW is the thickness of the plate as described previously. Now, how do we determine V sub Tf, which is the post-critical buckling strength? Now, you can see that on the right hand side of the picture, the girder that I tested here, there is a formation of tension band. So, basically the tension band also creates what is known as plastic hinges formation, as you can see on the right hand side, which is described pictorially. The spacing between the stiffeners is defined as C, the depth of the web is defined as D, and the top is basically defined as the compression flange and bottom is defined as the tension flange. So, the total shear at failure is defined as V sub Tf, and the resistance to shear buckling after critical buckling stress. Basically, after buckling, the vertical shear is resisted by a combination of two things. One is the formation of tension band due to post-critical buckling. You can see the tension band here, the one that is highlighted between two parallel lines. The arrow marks are showing the formation of the tension band, and the yield zone is basically in between and is also known as the tension band, and the anchorage point is S sub T for the bottom flange. Basically, it denotes the anchorage or the distance between the two plastic hinge formation at the tension flange, and then what you see at the top is S sub C, which is also the anchorage point. Basically, the distance between the two plastic hinges formation at the compression flange, one at the compression flange and another at the stiffener location, which is denoted as S sub C. So, S sub C and S sub T is the anchorage lengths due to tension field action, and the contribution of the anchorage lengths and the formation of plastic hinges also contributes to resistance to shear buckling after critical buckling stress, and it is denoted as formation of plastic hinges within the flanges. So, the plastic hinges are denoted here at the top as well as at the bottom. Note, we need to understand that the contribution to resist vertical shear due to formation of plastic hinges depends on the thickness of the flanges, that indirectly contributes to the plastic moment capacity as well as the stiffness of the flanges. Now, how do we estimate the formation of tension band due to post-critical buckling? So, let us look at this figure here. The illustration of post-critical buckling to determine the shear strength of web in plate girder with thin webs can be demonstrated by showing the picture here. You can see a girder simply supported and a concentrated load is applied at the center, and you can see that there are intermediate transverse stiffness that are located approximately equal to the depth of the section, and you can see the formation of tension band. Basically, the tension is forming here. This tension field in individual subpanels can be seen here. This can be idealized as an equivalent end truss as you see below. The compressive forces are taken by the end post as well as the intermediate transverse stiffness that you can see. The diagonal band is basically known as the tension field tie. Now, let us look at how the shear strength of web governed by shear buckling as per IS 800-2007. Two methods are provided in IS 800-2007 to determine the nominal shear strength V sub n of web plate with or without intermediate stiffness. One is called the simple post-critical method, another is called the tension field method. In simple post-critical method, it is based on the shear buckling strength that can be used for web of I-section girders with or without intermediate transverse stiffness, provided that the transverse stiffness are the supports. So, the nominal shear strength is given by Vn equal to V critical, where V critical is the shear force corresponding to web buckling, and it is defined as Av into tau B, which is equal to D into Tw, which is the shear area, into tau B, where tau B is the shear stress corresponding to web buckling, which is equal to Fy divided by root 3 for lambda sub w less than or equal to 0.8, and it is equal to 1 minus 0.8 into lambda sub w minus 0.8 into Fyw divided by root 3 for lambda ranging between 0.8 and 1.2, and it is equal to Fyw divided by root 3 into 1 by lambda w square for lambda sub w greater than 1.2. Now, the lambda sub w is basically the non-dimensional web slenderness ratios, which is defined as root of tau yw, which is the yield strength in shear divided by the critical elastic buckling strength in shear. So, that can also be represented as Fyw divided by root 3, because tau yw equal to Fyw by root 3 into tau critical E. So, here the tau critical E is the critical stress of the plate under shear loading, which can be defined as K sub V, which is the elastic critical buckling stress coefficient, into pi square E divided by 12 into 1 minus mu square into D by T sub W to the whole square. So, the elastic plate buckling coefficient under shear loading, as I described previously, is K sub W, and it is equal to 5.35 when the transverse stiffness are provided only at the supports, and it is equal to 4.0 plus 5.35 divided by C by D the whole square, which is the aspect ratio of the plate web panel for C by D less than 1.0, where C is defined as the stiffness spacing and D is the web depth. For C by D greater than or equal to 1.0, you have another equation, which is 5.35 plus 4.0 divided by C by D the whole square. Now, why does IS 800-2007 consider tau sub B instead of tau critical E? It is very natural to think that it is shear buckling, so you should consider only tau critical E rather than tau sub B. The tau critical E here is defined as Kv into pi square E divided by 12 into 1 minus mu square into D by Tw the whole square. Now, let us look at why that is the case. So, if you plot the shear stress versus the slenderness ratio of the web, you can see that you get a nice Euler curve, which is defined as tau critical. You can see that the Euler curve is dotted after a certain point and then it is solid below a certain point. You will understand quickly why it is the case. You can see that it cannot increase or exceed tau sub y, which is the shear stress in yielding. So, it has to be cut off at that location, and then tau y we know that is Fyw divided by root 3. Now, we also define a point as point C, which is corresponding to 0.64 of tau sub y, and the corresponding lambda sub w is equal to 1.2. Now, we have another point B, and the lambda sub w corresponding to that is 0.8. That point B is basically the starting point of the inelastic buckling, and the region between B and C refers to inelastic buckling. So, now when we connect the dots, we have B to C is basically a linear transition zone, and after C it is taken over by the Euler buckling stress equation. To the left of B is basically the 100% yielding or the plastic zone, and so you have AB, which is basically completely fails by shear yielding. B to C it fails by inelastic buckling, and C to D it fails by elastic buckling. So lambda sub W less than or equal to 0.8, it is a thick webs and it is shear yielding due to thick webs, and to the right of lambda sub W, which is greater than 1.2, we have thin webs. Now between B and C we have intermediate webs, and the intermediate webs fail due to a combination of shear yielding and buckling, leading to inelastic shear buckling in the intermediate range of thickness. Now tension field theory. The tension field theory, basically there are three components that contribute to shear strength of the web, which is V ultimate. First is the primary buckling strength of plate due to elastic critical stress of the plate, which is VCR. The second one is tension field action of the web. The third one is the plastic moment capacity of the flanges. The first one is basically described as stage 1, the second one is described as stage 2, and the third one is described as stage 3, right. Stage 2 and stage 3 contribute to what is known as VT, and Basler in 1961 was the first to formulate a successful model for tension field action for the plate girder, and he came up with this equation tau sub S equal to tau critical E plus 0.5 FYW into 1 minus tau critical I divided by tau YW into sin phi. He also assumed that the inelastic buckling will occur if tau critical E exceeds 0.8 tau YW, and defined an inelastic buckling stress tau critical I as tau critical I is equal to 0.8 tau critical E into tau YW the whole power 0.5 for 0.8 tau YW and 1.25 tau YW. So this tau critical E fluctuates between 0.8 of the shear yielding and 1.25 of the shear yielding. Basler's formula overestimates the shear strength of a plate girder whose flanges are incapable of supporting lateral load from the tension field. It does not take into account the formation of the plastic hinge in the flanges, and hence it overestimates the shear strength of the girder. It gives the shear strength for a complete tension field instead of a limited band as observed in the test. This is taken from the book Gaylord 1998, and the source is basically the paper published by Gaylord in 1963, which is described as the discussion of K. Basler, strength of plate girders and shear, and published in Transactions of ACE volume 128 part 3 page 712. Now here you can see that there is a formation of tension band on the right hand side. This tension band basically is represented by the tension stress F sub T, and it makes an angle of phi with the horizontal axis. Now the drawbacks of tension field model proposed by Basler can be summarized as: the ultimate shear strength of web differed from Basler's model due to boundary conditions of the web, inclination and width of the tension field, and tensile stress distribution within the tension field. Following Basler's tension field model, Porter et al. 1975 proposed a model referred to as the Cardiff model. As you can see on the right hand side, this is the Cardiff model, which is now used all over the world for shear capacity due to tension field action. So you can see that there is a compression flange, there is a tension flange, there is a formation of plastic hinges that takes place, the stiffener spacing is given as C, the depth of the gird is D, S sub C and S sub T is equal to the anchorage lengths of the tension field, VTF is the total shear at failure. And we can also see the F sub T, which is the tensile field stress at yield. So it accounts for the effect of bending stress of the flanges on the width of the diagonal tension band. The diagonal tension field is composed of a central part that anchors on the transverse stiffeners. You can see that anchors on the transverse stiffeners and the right hand side of the picture, and two additional parts anchored on the flanges that is defined here, one on the compression flange and one on the tension flange. So from the tension field theory as per Cardiff model, we can understand that after the web buckles along the direction of principal compressive stress, which is F of phi plus 90, as you can see from the figure down, a new load carrying mechanism is developed along the principal tensile direction called tension field action, which is F sub phi. It offers resistance against any further increase in shear load. The tensile field is constituted by the portion of the plate, which is F sub T. So the tensile field consists of web plate in the principal tensile direction anchored at the top and bottom flanges and stiffener members. The total web stress combines critical shear stress at buckling tau critical E and post buckled membrane tensile stress F sub T due to tension field action. Hence, post buckling strength contribution due to tensile stress F sub T is found using von Mises failure criteria. Let us resolve stresses along and perpendicular to the angle of inclination phi for the final stress state. Now, the stresses are F of phi plus 90 and tau of phi, and using Mohr circle concept, we can find out F sub T, which will be described in the next slide. So, finding the stresses F of phi plus 90 and tau of phi using Mohr circle concept. Here the radius of the Mohr circle is tau critical E, which is given as kV into pi square E divided by 12 into 1 minus mu square into d by t the whole square. And you can see that in the x-axis it is F and it is in the y-axis it is tau, and it is making an angle of 2 phi, and the radius is defined as tau critical E. So, the horizontal component of that is F of phi, and now using the r theta concept, we can see that F of phi equal to tau critical into sine of 2 phi for small values 2 phi equal to sine 2 phi, and F of phi plus 90 degrees is given as minus tau critical E into sine of 2 phi, and tau phi is shown here at the right side, which is quadrant 4 as well as the quadrant 2, and tau phi is given as minus tau critical E into cos of 2 phi. Now, the stress state on the web plate is shown here, which is basically compressive stress F of phi plus 90, the tensile stress is F of phi, and the shear is tau phi. Now, the Cardiff model is shown on the right hand side. Now, we can see that this results in a tensile force or a tensile stress F of T acting in the diagonal direction, and which should be included along with F of phi. Now, we have F of phi equal to tau critical E into sine 2 phi plus F of T. Here, there are two unknowns, phi as well as F of T, which we will find out in the next slides. Now, finding F of T. The von Mises yield criterion is given as F of phi square plus F of phi plus 90 square minus F of phi into F of phi plus 90 plus 3 into tau phi square is equal to Fyw square, which is the yield stress of the web. Now, let us substitute F of phi plus 90 and tau of phi in the above equation to obtain F of T. So, when we do so, we get a big equation here, which is tau critical E into sine 2 phi plus F of T the whole square plus of minus tau critical E into sine 2 phi the whole square minus of tau critical E into sine 2 phi plus F of T into minus tau critical E into sine 2 phi plus 3 into minus tau critical E into cos 2 phi the whole square, which is equal to Fyw square. Now, we can expand this equation here, a plus b the whole square equal to a square plus b square plus 2ab, and similarly when we do all that stuff, we get a big equation. Now, we can add the common terms, which is tau critical E into sine 2 phi the whole square is occurring 3 times here. So, that can be 3 times tau critical E into sine 2 phi the whole square. Similarly, we have 2 tau critical E into sine 2 phi plus one more term, which is basically F of T into tau critical E into sine 2 phi. So, we have 3 tau critical E into sine 2 phi into F of T. So, when we do so, we have 3 into tau critical E sine 2 phi the whole square plus Ft square plus 3 tau critical E sine 2 phi into F of T plus 3 into tau critical E into cos of 2 phi the whole square into Fyw the whole square. So, now we can take out the common terms, which is 3 into tau critical. Now, when we take that out, we have sine of 2 phi square plus cos of 2 phi square, which becomes 1. So, the equation gets further simplified, as you can see below. Now, we can rearrange the terms such that it is in the form of an quadratic equation. So, the roots of the algebraic equation ax square plus bx plus c equal to 0 equal to minus b plus or minus root of b square minus 4ac by 2a. So, here a equal to 1, b equal to 3 into tau critical E into sine 2 phi, and c equal to 3 into tau square critical minus Fyw square. So, when we do this equation, we have F of T is given by this big equation here. We simplify this further by taking half outside, and then we are doing many more things. We are taking that 4 within the bracket outside. When we do so, that 4 becomes 2, and already there is a half, then 2 by 2 becomes 1, and we have that F of T equal to minus 1.5 tau critical E into sine 2 phi plus root of Fyw square plus 2.25 into sine 2 phi the whole square minus 3 into tau critical square. So, now we multiply and divide with Fyw. So, when we do so, we get another equation here, as you can see, and this becomes equation 1. and when we do so, one more time multiply here with the entire equation with f of t, we have f of t divided by fyw is equal to minus 3 by 2 tau critical E into sin 2 phi divided by fyw plus this fyw outside the bracket goes inside the bracket, as you can see here. Now let us substitute fyw equal to root 3 into tau yw. So when we do so, we get another equation here, and then finally we get the one that is highlighted in the rose color, which is ft divided by fyw equal to minus root 3 by 2 into tau critical E divided by tau yw into sin 2 phi plus root of 1 plus tau critical by tau yw the whole square into 0.75 into sin 2 phi the whole square minus 1. Now let us find out the value of shear strength Vt due to post-critical behavior, that is tension field plus plastic hinges. By equating the external and internal work done, the first one is the external work done by post-buckling shear load V sub t that causes the mechanism to develop. The next one is the external work done by the vertical component resultant of tensile stress F sub t due to tension field. The third one is the internal work done at the 4 plastic hinges. Now let us look at the external work done by post-buckling shear load V sub t that causes the mechanism to develop, which is equal to V sub t into St into theta. Here you can see that due to the rotation of the plastic hinges, we can see that there is a movement of S of t into theta that you can see at the right side of the picture. That is basically the vertical movement due to the rotation of the plastic hinges. So we have V sub t into St into theta. So that is the external work done, which is force into the distance. Now the second external work done by the vertical component resultant of tensile stress F of t along xy due to tension field. What is xy? We will understand what is xy by seeing the picture here. So you can see that xy is basically the distance between the two plastic hinges, one is at x and one at y. One x is at the top and y is at the bottom, and you can see that the phi is making an angle with regard to this tensile stress F of t, and the anchor distance at the top is S sub c and the anchor distance at the bottom is S sub t. So now we have the force F of xy. Now let us look at it very carefully here. The resultant force is F of xy is basically minus F of t into sin phi, which is the vertical component, the stress, and it has to be multiplied by the tension bandwidth. The thickness of the tension bandwidth is basically T, which is the web thickness, into Yp, which is the width of the band. Now, due to vertical displacement, xy undergo a upward displacement S of t into theta. Now, the external work done by the vertical component from tensile stress F of t is given as F of xy is minus F of t into sin phi into T into Yp into S of t into theta. The negative sign indicates that it is a downward direction or the force is acting downwards. Now, we have the first one that is done, which is basically Vt into S of t into theta. The second one is minus F of t into sin phi into T into Yp into St into theta. So, the total external work done is V of t into S of t into theta minus F of t into T into Yp into sin of phi into S of t into phi. Now, the internal work done at the 4 plastic hinges is basically 4 into MPF into theta. Now, equating the external and internal work done, we have V of t into S of t into theta is equal to F of t into T into Yp into sin phi into S of t into theta, which is basically the left hand side goes to the right hand side. So, negative becomes positive plus 4 MPF into theta. Now, we can find out V of t equal to F of t into Yp into sin phi plus 4 MPF by S sub t. Now, the unknown in this one is the Yp, which is basically the tension bandwidth. Now, how do we find out that? Now, we can revisit the same figure that we saw in the previous slide. You can see on the right hand side. So, Yp is basically given as Oy into sin phi. Okay, so which triangle are we looking at now? Yp equal to Oy into sin phi, right? Okay, so we are looking at the smaller triangle here, which is Yp is equal to Oy into sin phi, because sin phi equal to opposite by hypotenuse. So, we have opposite is equal to sin phi into hypotenuse. The hypotenuse here is Oy. Now we can also write OY as OA minus C plus S. So if you look at the geometry here, OA is the line that connects from O to A, minus C that gives you the dotted portion, and then we should also add S, which is the distance between Z and Y here. So when we do so, we get OY. Now from triangle XOA, which is XOA, the larger triangle, we know that tan phi is opposite by adjacent. The opposite here is a D, the adjacent is OA. Now this tan phi can also be written as cot phi, which means that cot phi equal to 1 by tan phi, which is equal to OA by D, because cot phi is inverse of tan phi. So we have cot phi equal to OA by D. Now OA equal to D into cot phi. So we can substitute that. We have OY equal to D into cot phi minus C plus S. Now substituting OY into YP, we have YP equal to D cot phi minus C plus S into sin phi. Now let's keep this for some time. Let's go back to the original equation. The ultimate shear strength governed by shear buckling is V ultimate, which is given as V critical plus V sub T. So the V critical is tau critical into dt. Now Vt equal to F sub T into Yp into sin phi plus 4 MPF by S. Now let's substitute Yp in this above equation. We have Vt equal to F of T into D cos phi minus C plus S into sin, which becomes sin square phi plus 4 MPF by S. So we have V ultimate is equal to tau critical into D into Tw plus F of T into Tw into D cot phi minus C plus S into sin square phi plus 4 MPF by S. Now this becomes equation 2. Now let's look at the stresses and moments on the compression flange. So on the compression flange, you can see the anchor distance S, and there are two hinges there, MPF and MPF, that are acting here. So the moment about X is given as 2 MPF, which is equal to Ft into Tw into S into sin phi. Ft into Tw is basically the stress into the thickness into S sin phi. Basically we are looking at the vertical component, which is given as S into sin phi. Phi is the angle that makes with the horizontal direction, and since it is an uniformly distributed load, we have to find out the lever arm distance. So the lever arm distance is the distance divided by 2. So it becomes S into sin phi divided by 2. So now we have 2 MPF equal to Ft into Tw into S square by 2 into sin square phi. So we have the anchorage distance S is given as S equal to 2 divided by sin phi into root of MPF divided by Ft into Tw. Now substituting the value of S and divide by Vyw on both sides, where V sub Yw is equal to D into Tw into tau Yw, and tau Yw is given as Fyw divided by root 3. So when we do so, we get a big equation here, and we can do some algebraic juggling, and you can get an equation as you can see here again, and we substitute the value of S as you can see in the green color highlighted portions in the equation. We can see that we can modify the equation such that both the terms can be added together, the third and the fourth term, as you can see here. And when we add the term, we get 4 into root 3 into sin phi into root of Ft by Fyw into MPF divided by D square into Tw into Fyw. Here we have MPF is the plastic moment capacity of the flanges, which is given as Zp into Fyf. Zp is the plastic section modulus multiplied by the yield stress Fyf, which is given as Bf into Tf square divided by 4 into Fyf, where B sub f is the width of the flange and Fyf is the yield strength of the flange. So when the high axial force are developed in the flanges, the effects will reduce the plastic moment capacity of the flange, because the plastic moment capacity should take care of the high axial force, and the remaining portion can be used for the contribution of anchoring the tension field band. So after accounting for the axial force N sub f in the flange due to overall bending and any external axial force in the cross section as follows, we have MFR is given as 0.25 Bf into Tf square into Fyf bracket open 1 minus Nf divided by Bf Tf Fyf divided by gamma m naught the whole square. This basically gives the remaining moment that is required to help in the formation of tension field band, that is for the stage 3 as a result of the formation of plastic hinges in the flanges. So, the above equation that you can see on the left hand side shows the summation of three components of shear resistance. The first one is the web buckling due to critical stress, which is tau critical. That is the first equation that is highlighted in red. The next one, which is highlighted in slightly in a cyan color, which is post buckling membrane yield strength of the web plate. As you can see, that is root 3 into sin square phi into Ft divided by Fyw into cot phi minus C by D. The third one is the plastic moment capacity of the flanges, which is in the blue color, which is 4 into root 3 into sin phi into root of Ft divided by Fyw into Mpf divided by d square Tw into Fyw. This equation can be solved only if the value of phi is known. By a series of parametric studies, Evans 1983, Evans was basically the doctoral advisor for my master's advisor, Professor N. Shanmugam, who did his PhD under Professor Evans at Cardiff University, and Evans in 1983 has given an approximate value of phi as phi equal to 2/3 of tan inverse d by c. Now, from equation 2, we have V ultimate equal to tau critical d into Tw plus Ft into Tw into d cot phi minus c plus s into sin square phi plus 4 Mpf by s. From equation 1, we have f of t, we have to recollect. So, if you go back few slides back, you will get the value of equation 1, and f of t, which is the equation 1, is given as minus 1.5 tau critical E into sin 2 phi plus Fyw into root of 1 plus 1 by Fyw the whole square into 2.25 into sin 2 phi square minus 3 into tau critical square. Now, this can also be rearranged, okay, as you can see here, and you can do some mathematical jugglery, and when we introduce the term psi equal to 1.5 tau critical E into sin 2 phi, to simplify this f of t equation, we get f of t equal to minus psi plus root of Fyw the whole square plus psi square minus 3 tau critical square. Now, taking WTF equal to d cot phi minus c plus s into sin phi in equation 2, we have that is equal to d cos phi minus of c minus s into sin phi. Now, we are basically multiplying the entire term with sin phi, and cot phi is basically cos phi by sin phi. So, sin phi and sin phi gets cancelled. So, cos phi remains. So, this equation becomes d cos phi minus of c minus s into sin phi. Now, substituting these values in V ultimate and taking AV equal to d into Tw and tau critical equal to tau b, we have V ultimate equal to AV into tau b plus Ft into Tw into WTF into sin phi plus 4 Mpf by s. The first term is basically the stage 1 due to elastic critical buckling stress under shear loading. The second term is stage 2 due to tensile field action alone, which is Ft into Tw into WTF into sin phi. The third term is the stage 3 due to full plastic hinge formation, which is 4 Mpf by s. Does IS 800 adopt the same form of equation for thin plates governed by shear buckling? It's a question that we need to answer. So, V ultimate, as we described, AV into tau b plus Ft into Tw into WTF into sin phi plus 4 Mpf by s. So, when we look at IS 800, the right hand side, which is a screenshot shown, refer section 8.4 of IS 800, we can see that the term AV into tau b plus Ft into Tw into WTF into sin phi is basically represented here, that is shown in the yellow color highlighted marks. But there is a small difference, there is a reduction factor of 0.9 that is applied, and here we have psi equal to 1.5 tau critical into sin 2 phi, and you can see that similar equation is also there in IS 800, and Ft equal to minus psi plus root of Fy square plus psi square minus tau critical square, f of t equal to minus psi plus root of Fy square plus psi square minus 3 tau critical square, which is also shown in the right hand side of the equation, except that instead of f of t, it is f of v. Basically, the meaning is same, yield strength of the tension field obtained from the equation. Now, WTF is equal to d cos phi minus of c minus s into sin phi, which is also shown here, but there is a slight difference here. The one that is shown on the figure is basically an older version, an errata that came out, which basically says that instead of the above equation, substitute d into cos phi minus of c minus s sub c minus s sub t into sin phi. So, basically instead of plus, we have to substitute minus, and this is basically an error in the printing mistake of the code. A similar equation is also existing. So, what we derived in the equations is basically the same as the one that is present in IS 800, except that here in IS 800 they have two A sub C and A sub T. So, two anchorage points, one corresponding to compression and one corresponding to tension. Here we are using only S, basically a common anchorage length. Now, phi is given as 2/3 of tan inverse D by C, which can also be represented as tan inverse D by C by 1.5. Here also there is an error in the IS 800. As you can see, the highlighted portion does not contain 2/3, but in reality it is tan inverse D by C divided by 1.5. This also is basically from the errata for IS 800. And we have S equal to 2 by sin phi into root of MPF by FT into TW, which is very similar to the value that is given here, highlighted in the red color box on the right hand side. So, this MPF is basically represented as MFR in IS 800. It takes into account the reduced plastic moment capacity of the flanges, which is given as 0.25 into BF into TF square into FYF bracket open 1 minus N sub F divided by BF TF FYF divided by gamma m naught the whole square. So, this is the same equation that is given also in IS 800, as you can see on the right hand side, marked in a red color box. So, MFR is basically the reduced plastic moment capacity of the flange plate. Now, how do we take this into consideration? So, recall table 10 of IS 800 here. You can see for the built up member, the last section is given here. So, there is an option of taking compound steel sections. So, that leads to buckling class C, and we can also take option 2, which we described as welded plate girders. Here you can have buckling class B, C or D, but not buckling class A, because due to welding you have enormous amount of residual stresses that we have described in the previous lectures, and as a result the code penalizes you for using welded sections, and hence it says that you should not take buckling class A, rather you can take buckling class B, C or D, as you can see here, but it depends upon the thickness of the flanges and the direction in which it is buckling about. So, if it is plate with thickness less than 40 mm and buckling about the major axis ZZ, so you can get the curve B, and if it is buckling about Y by, it is curve C, and if the thickness of the plate is greater than 40, then B and C becomes C and D, as you can see, that is highlighted in the left hand side of the picture. Now, what is the significance of buckling classes? You can see on the right hand side the original equation that was developed and proposed by the European multiple column curves, and you can see that there are 4 such classifications starting with A0, A, B, C and D. So, with increase in imperfection magnitude, the curve which is convex eventually turns into concave, as you can see here on the curve, and you can see that in Indian classification IS 800 we do not have A0, we start with A, B, C and D, the buckling class, and curve B is for welded box section, as you can see on the right hand side, that is color coded. And then you can also have I sections, which is flame cut and buckling about minor axis, or you can have welded H sections, which is universal mill cut and it is buckling about major axis. Similarly, rolled steel sections with welded cover plates, you can see it is buckling about major axis, and you have curve D, which is for heavy shapes. So, when you look at the magnitude of imperfections, there is an increase in the imperfection which leads to decrease in the axial capacity. So, when the imperfections move from A to B to C to D, which is an increase in imperfections as a result of both geometric as well as material property, which is classified here in terms of A, B, C and D. A being a superior cross section with less imperfection, and D being an inferior cross section with more imperfections. So, as imperfections increase from A, B, C to D, there is a decrease in axial capacity which is going the same direction. That is also denoted by the arrow mark, that is going from convex to concave. With this one, we end this discussion on plate girder theory, and we will get back to you in the next class with more such discussions. Thank you very much.